All right, let's get some administrative things out of the way to start. We have our exam 3. So exam 3 is actually going to be November 16th, which is on a Wednesday. So I believe that's next Wednesday? Yes. Next Wednesday. All right, that's our exam 3. Unfortunately, on 11/11, which is this Friday, is the drop date. Oh, wonderful. Which means that you have to make a call if you feel like you're in a position where you don't want to take a bad grade in this course or something. You have to decide by Friday if you want to stick it out, but then, it'd be nice if that exam 3 was going to be on Wednesday, right? This Wednesday, because then you would at least know. But we just have more material that we have to cover, so that's your drop date.
Can you just give us a test Wednesday on what we've already done?
No. Yeah, I don't want to throw a test in all of a sudden. So that's the situation. All right. So if you're concerned about your grade or like what you need to pass or anything, just get with me. All right. I did update the grades today, and I've dropped 2 quiz grades. So your 2 lowest have been dropped, which brought your average up a little bit. And I want to talk about this exam 3. This exam 3 is going to cover everything after exam 2, which will be derivatives of exponentials and logs, L'Hopital's rule. Okay, we know that's a big section right there. And then max and min values. So finding the max and min on a closed interval, and then finding local max and mins like we've been doing, right? Like the homework section for 4.3. And then there's a graphing portion. And the graphing portion is very long, right? These problems are even longer than what we did last class. So what I've decided to do is I'm giving you 4 problems. I'm giving them to you today. These are take-home problems. These are exam problems. And these are due on the day of the exam.
So that's
all right.
Going to go towards the test?
This will go towards the test. Don't ask me what percentage yet, because I don't know how long the rest of the test is. But I'll let you know within the next class or 2. So please take one of these. Pass them.
Can we get help for you on that?
Yeah, let me pass them out, and then we'll go through the instructions.
Why do I have
There's an extra one there in case there's someone else. If not, just leave it.
Everybody, we're meeting at Starbucks tomorrow.
Here you go.
Oh yeah, we do get extra points if we meet outside of class.
Okay, so let's go through this. The very first instruction here, work alone. Getting help or working with other students will be considered academic dishonesty, and you'll receive a 0 on the entire exam. If you need help, you may come to me only. All right, that means reach out to me if you're working on a problem, you want to know if you're on the right track. One thing that a lot of my internet students do is they just kind of like take a picture of their work and then they text me. And my cell phone number is on the syllabus, so you can just say, hey, does this look right? Just make sure if you're going to do that, let me know who you are. All right, tell me your name and what class you're in. That way I can know who I'm talking to. Show all of your work in steps. So no work, no credit. Follow the steps outlined in class. So I'm going to outline those steps today. And I also plan on handing you, I'm thinking I want to do this, kind of like a template. Do you remember that template we had for the word problems? Like a template that you would use for each problem. So you would have 4, I'm going to give you 4 templates, and you fill out those templates for each of these 4 problems. I just didn't have time to get it. I had it created, but I didn't have time to print it. So that's my plan. You can get started on this now, though. Yes?
Can you post it today? Like in the files or something?
You know what? That's a pretty good idea. Instead of handing it out, just post it. Then have you print it. Yeah, we'll see. Let me see if it's the final clean version I want. for now you can at least get started, because here's the idea. You should do all your work on separate paper and work the whole thing out, get a nice graph or whatever. Once it's all done, transfer it onto a nice, clean, final version. That's what I mean here on this step. Do all your work on separate paper. It should say your work, sorry. You work. Your work must be clean and neat, a final version. So I don't want to see your mistakes and your eraser marks and your scratched out things and stuff everywhere sideways along the margin of the page. I want to see a nice, clean set of work. Make sense? It's due at the beginning of class on the day of exam 3, which is the 16th, next Wednesday. Staple your work in order and use this as a cover sheet. So I expect you to have this sheet on top, and then number 1 followed by number 2, followed by number 3, and then followed by number 4. Okay? Any questions on that? This is part of the exam. All right? I don't know what portion. I'm thinking 30%. That's my gut right now on this, 30%. It could be as high as 40. Okay? All right, and then the in-class part that you do on Wednesday, I will not ask you to graph anything. Well, I'm sorry, I will not ask you to go through all of these steps that we're going to go through today. So this is curve sketching. This is 4.4. 4.3 is the homework that you had last time. A problem like that could appear on the test, and we saw those were long, right? So you might get one of those on the test. But if I give you one of those on the test, I'm going to keep it pretty clean, all right? In other words, like, the algebra is going to be pretty nice. Not going to be one of the harder problems that I know is going to take a long time. What I'm really going to be focusing on this exam 3 is, do you know the derivatives of exponentials and logs? Can you apply L'Hopital's rule? So I would say a majority of the test is going to be L'Hopital. And then closed interval method, you're going to have to demonstrate you can use closed interval method. And then the 4.31 problem. So we'll talk about that a little more maybe on Monday next week. Yeah, and we saw that there's, you know, it took us 2 days, maybe 2.5 to get through L'Hopital.
It's just all those different.
Yep, you could have, you know, 0 to the 0, and, you know, you have to bring in logs on both sides. And that's another thing with derivatives of exponentials and logs. Don't forget there's also logarithmic differentiation in there. That's also a technique. That's where you have to bring logs in on both sides, but that's not the limits. It's for taking derivatives. So I'll leave it to you to go back and review, but that's where we're headed. Today is 4.4. All right, that's what we're going to do. And then on Wednesday, we're going to start a new section. I would like for everyone to watch the video for 4.5. Make sure for next class you watch the video for 4 or 5. All right, we're going to start word problems, and because it's word problems, what I do in the course video for 4 or 5 is I kind of set up a lot of the word problems. I show the geometry of them, and then when we come to class, my plan is to just go after the problems. All right, and I don't want to have to like re-explain like what we're trying to do. All right, good. All right, 4, 5. And there's no mean value theorem on this test. So we are at curve sketching. Oh, and optimization will be on the test. Forgot to mention that. So that we haven't covered yet. That's what we're going to cover Wednesday and on Monday. We're going to do 2 days of optimization. All right, here we go. So when it comes to curve sketching, we've actually done a lot already in terms of curve sketching. Did everyone get one of these? Did you get one?
Yeah, I don't.
Okay. We've done a lot of what we're going to be doing today with the curve sketching, using the first derivative to see where a function is going up and down, second derivative to figure out the concavity, and then we did draw graphs, right? All we're going to do is add some things in here now that we get from college algebra, and a couple of other things that we learned in this class already. So these are the suggested steps that I have for curve sketching, and I want you to understand that for all of these steps, it's find the domain I mean, you should be able to find the domain of the function. That shouldn't be an issue, all right? But things like finding the x-intercepts and y-intercepts, you're going to do that if you can. In other words, if the algebra is clean and the equation you're trying to solve is solvable, like we have a technique for it, then you're going to go ahead and do it. And the book even says that. Like, do it if it's not too hard. Now, what's too hard? You know? Things like checking for symmetry. That's to see, like, does the graph look like a reflection of itself over the y-axis or something like that. Finding asymptotes. So these are all things, steps 1 through 4, these are all things that we would have done in like a college algebra class. And then steps 5 and 6, that's what we've already done, right? Where is it increasing, decreasing? Find the max and mins. Where is it concave up, concave down? Then making a table and sketching the graph. That was that table that I made in class where we had the 3 rows, remember? So really, all today's about is this steps 1 through 4. We're adding that to the problem. All right? So let's go ahead. That's it. Let's start a problem. I did not make a homework solution video for this section. And I just haven't gotten around to it. I don't know if I'll get around to it. That's going to be several hours of work. So what I've decided to do today is just do some problems out of the section that I think will be a good enough guide to get you through these 4 problems. All right? So the first problem that I'm going to do is I want to look at y equals, and by the way, this is number 14. No. I'm going to do number 16. X over x cubed minus 1. I would like to sketch this function. So this is just like this handout you have right here. The steps that I'm about to do are what I expect to see on this take-home. The first step, all right, the first step is the domain. So step 1, what's the domain of this function? Everything except x is 1. So when we look at this, we say we can't have division by 0, right? That would be a problem to have division by 0. So what we could do is we could set the denominator equal to 0, solve it, and we would get 1. So we know that 1 can't be there, right? So how do we say everything but 1? Well, we could do it this way. Negative infinity to 1 union 1 to infinity. Think about the number line. That's everything on the number line except for the number 1, isn't it? We've yanked that number 1 out, kind of jumped over it. You could also put x is not 1. Okay, that would also be a shorter version. But in the book, if you do some problems out of this section, you go look at the solutions in the back of the book. They're going to use interval notation for domain. So that's what I'm going to use. All right, that's the first thing. The next thing we want to talk about are the intercepts. The x and the y-intercepts. So for x-intercepts, do you remember from all of your other math classes how you find the x-intercepts of a function? You set the function equal to 0. So I'm going to take this function and I'm going to set it equal to 0. And now we just set the top equal to 0 because we've already learned from when we were doing derivatives that a fraction can only be 0 if the top is 0. So this would mean that only x can be 0. That's the only way that'll happen. And, well, that's my answer, right? So when I draw my graph, on the x-axis, I should have an x-intercept at 0. A dot, right? A point. How do we find the y-intercept? Plug in 0 for x. So that's like f of 0. You plug in 0. And let's try that. Plug in 0, you get 0 on top. 0 minus 1, that's 0 over negative 1. That's just 0. Now you're not asked right now to draw a picture. But if we did, right now, here's what we'd know. The origin is part of our graph, right? The x-intercept and y-intercept are actually the same point in this problem. Not always, but in this problem they are. Okay? All right, that's step 2. Let's go and look at these notes. What's step 3? Check for symmetry. All right, now when it comes to symmetry, I know for a fact that a lot of you are going to have some holes in your math when it comes to symmetry. So I'm going to put the step up here for symmetry. And I'm put a star next to it. And what I mean by the star is that when you do this at home, if you check for symmetry, I will consider that to be like bonus, all right? I'm not going to expect symmetry to be checked. And really the reason is we don't actually need it. It's not absolutely important to be able to get the graph, but it helps us sometimes to know whether or not this is symmetric. Let me give you a quick example of something that's symmetric. A parabola is symmetric over the y-axis, right? There's symmetry there. And so we say that's symmetric over the y-axis. Then you have something like x cubed, which looks like this. That is not symmetric over the y-axis, right? If I flip this over, it's not over there, right? If I flip that over, it's not a mirror image of itself. But if I do a double flip over y and then take that over x, I do get symmetry. And this is called symmetry over the origin. All right? Another example of this would be, let's see, if you look at the cosine curve. The cosine curve, that's what cosine looks like, is symmetric over what? The y-axis. How about the sine curve? This is like a quick crash course in symmetry here. Is that one symmetric? It's a double one, right? If I take this like this over on this side, then it would go like this, wouldn't it? If I just flipped it over the y, and then if I take that and I flip that over the x, it's going to be the same thing on the other side, isn't it? So this one right here, which was, this was y equals x cubed, right? And this one right here, which was sine x, are both symmetric over the origin. This one right here, which is x squared, and this one right here, which is cosine x, right, are both symmetric over the y-axis. And so what we can use to tell whether or not a function is symmetric over the y-axis or symmetric over the origin is to check whether or not the function is, does anyone know? Good, odd or even. That's how we do it. We check to see if it's odd or even. So look at this right here. X squared, that 2 is an even number, right? And do you remember from pre-cal them telling you that cosine was an even function? Yeah. Okay, that's kind of what makes them both the same in that sense. Even functions, that they're both symmetric over the y-axis. And then these two are odd functions. Sine is odd, and look, x cubed, obviously cubed is odd, right? So here's how we check. If f of x equals f of negative x, then f is even. And therefore, I know you don't like the 3 dots, Bailey. I think you even mentioned that before, didn't you? I did. Okay, then f is even. Therefore, it's symmetric over the y-axis. So what this means, I don't know if you've ever thought about this, but what this means is that if I take a function and I plug, let's say, a number in here, let's say that that's the number 4, okay? That I should get the same thing as if I plugged in what? Negative 4. So take a look at this even function. If I plug in 4 here, I'm going to be up here, right? But if I plug in negative 4, I'm going to get the same thing. And that's going to work for every value of x. So every dot that I get on this side should appear exactly on the other side. And that's what will make it even. Do y'all see that? Okay, same thing here. If I pick this number, plug it in. If I plug in the same number but negative, I'm going to get the same value. Good? You don't. You actually have to check it in general. So we'll take a look at it. All right, now the other thing is that it could be, instead of an even function, an odd function. And what you need for an odd function is this. If negative f of x equals f of negative x, then f is called odd. I'm sure that you saw this in college algebra. It's just been a long time. Therefore, you have symmetry. I'm just going to put symmetry, SYM dot, over the origin. And what we mean by that is the double symmetry, right? Double reflection. Reflect over y, then x.
So you'll never have it over the...
Okay, Bailey, so you tell me, could I ever have it over reflection over the x-axis? That's what you're asking, right? Is that possible? So let's say I have a function that does this. Could it ever be a reflection of itself over the x-axis? Why not?
Because it would fail the vertical.
It would fail the vertical line test then, right? Then it wouldn't be a function. Understand? Okay. So good question. I was actually going to mention it. I was hoping someone would ask me. So I'm glad you did. Thank you. Yeah. All right. So now let's now check this function for symmetry. All right. Let's check it for symmetry. What does your gut tell you? Does your gut tell you anything at all?
Odd.
Why do you think odd? Because you see the only powers you see on x are 1 and 3. So it's probably going to be odd. So let's try the odd one first. So I need to show that these two things are equal. All right? So let me start with the left side of this. What is negative f of x? Negative f of x is that function with a negative in front, right? So I can put negative and then x over x cubed minus 1. And I could go even further and just slide the negative on top. I could also slide it on bottom, couldn't I? But it's one or the other, not both. So that's negative f of x. Now let me ask you, what is f of negative x? So that means go in here and replace all your x's with negative x's. Tell me what you would get. Negative x on top, right? Over negative x cubed minus 1. So the top here is what? Still negative x? And what's the bottom? What's negative x cubed? That's just negative x cubed, right? Without the parentheses. If I take a negative number and cube it, it's going to stay negative. In other words, this. I'm just being super clear, make sure everyone's clear on this. That's what that is, right? And if I cube the negative 1, I get negative. And if I cube the x, I get x cubed. So this becomes negative x cubed minus 1. Are these the same? No, they are not. Right? It's not. These aren't the same. Right? This one has negative on top, negative on top. This one is positive x cubed minus 1. This one is negative x cubed minus 1. So we are not going to have symmetry over the origin. Understand? The only other thing we could maybe have is that it's even. So what I would need to do is check to see if this is equal to this. Well, what is this? We already know that, right? That's this. Is that equal to this? No. It is not. So it's not even, it's not odd. If somebody just gives you a function, it doesn't have to be even or odd. All right? There's a third option, which is neither. All right? So we do not have symmetry here. There is no symmetry. When we draw this, we're not going to have like, it won't look like a reflection of itself over the y-axis, or it won't look like a double reflection. It's not going to happen. Understand? Was that a no? You're good? Okay. All right, so that's step 3. Now step 4. What was step 4? Asymptotes. Now, when we look at asymptotes, there are 2 types we have to look at, vertical and horizontal. So let's start with vertical. A vertical asymptote, if you recall from college algebra, was this, this imaginary vertical dotted line on our graph that when our function approaches it, it gets like shot up to infinity or shot down to negative infinity. Right? That's what a vertical asymptote is. And the places that you have these are any places where you have division by 0 Not 0 over 0, but division by 0. So a fixed number over 0. Remember when we did this? Fixed over 0 in a limit? Fixed over 0 was either infinity, negative infinity, or did not exist. So we're looking right now, what we're looking for is fixed over 0. Do we ever have that happen?
Yeah.
Where?
At 1.
At 1. It happens at 1. At x equals 1, what we get is 1 over 1 cubed minus 1, which is 1 over 0, which is undefined, right? So we should have a vertical asymptote at x equals 1. So if we start, I'm gonna start drawing this even though I don't want you to. I'm starting to put things together. Here's what I know. I have an x-intercept and a y-intercept there, right? We knew that. I know that I have a vertical asymptote at 1, like this. And I know it's not symmetric. That's what I know so far.
So if it's not a fraction, then there's not a vertical asymptote.
If you don't have division by 0, correct. Now, how about horizontal asymptote? Does anyone remember from college algebra what the horizontal asymptote told you? Like, what did it have to do with, the horizontal asymptote?
If the power of the denominator was lower than the power of the numerator.
Okay, yeah, that's what we would do for rational functions, right? For rational functions, you could do comparison of the powers. But more generally, what I'm looking for is for horizontal asymptote, didn't it tell you what was happening on the left hand and the right hand of your function? It tells you what's happening on the left and the right. Like in college algebra, you may have had a function that did this. Flattened out like that, and maybe did something like that. And these were our horizontal asymptotes. They give us what we call the right-hand behavior and the left-hand behavior of the function. The way that we find these in calculus is not the method you just mentioned. It's this instead. We have to do two things. First, we need the limit as x goes to infinity of the function. And then the second thing is we take the limit as x goes to negative infinity of the function. And I want you to just think about those limits, what they're telling you. The first one is saying, hey, look, tell me what the function's doing, right? As you let the x value take off to the right, right? Where is it headed? That's saying, what's the right-hand behavior? This one says, hey, what's the function doing as you take off to negative infinity, to the left? So that's going to give you the left-hand behavior. Do y'all see those two things? So let's do these two limits. So we have the first one, limit, x goes to infinity. We're evaluating that function, x over x cubed minus 1. And if I let x go to positive infinity, what do I get on top? Infinity. On bottom, infinity cubed minus 1, still infinity. Infinity over infinity? Bad. So, L'Hopital. I'm going to use L'Hopital, right? Because I can do that because it's infinity over infinity. So for L'Hopital, I take derivative of the top, 1. Derivative of the bottom, 3x squared. And now I try the limit again. What do I get here? Fixed over infinity. What does fixed over infinity go to? 0. Yes? Fixed over infinity. The top is 1, the bottom's getting huge, that fraction gets small. This goes to 0. This is a horizontal asymptote. It's the right-hand side. So this is, the function is headed towards 0, isn't it? It's headed towards 0. So you want to look at like the y-coordinate is headed to 0. 0 is the x-axis, isn't it? So out the right side, I should be heading towards the x-axis. What about out the left side? Does anything change? Let's take a look. You feel like we would, yeah? Yeah, so we're going to go to negative infinity. So what happens if I plug in negative infinity for x? Negative infinity over negative infinity cubed would still be negative, wouldn't it? Minus 1, still negative. Negative infinity over negative infinity. Take your derivative again, L'Hopital. Derivative of the top. Sorry, I shouldn't have put that right there. I had no idea why I put that there. That's bad notation. This was headed to negative infinity over negative infinity, right? Let me rewrite this. This is what the function was. It's headed to negative infinity over negative infinity, so I can use L'Hopital's rule. When I do this, derivative of the top is 1, but derivative bottom is still 3x squared. So nothing changed here, right? And are we still going to get fixed over infinity? Yes. So it's going to head to 0. So out both sides, it's headed to 0. Not always the case. Sometimes, headed out one side, it's headed to one thing. Headed out the other side, it's something else. Now that didn't happen in college algebra because it was rational functions. And all rational functions have the same horizontal asymptote out both sides. But if it's a different type of function, you may not have that happen.
So we do have an asymptote at horizontal at 0.
Yes, we want to look at it this way. Our left-hand behavior is to head towards 0. That comes from this.
Yeah.
Our right-hand behavior is to also head towards 0. All right, what's next? I have my asymptotes. That was step 4. Step 5, intervals increasing, decreasing. So now we're back to what we did last class. All right? Any questions? Step 5.
So those are going to be your horizontal and the vertical asymptotes going to 0?
No, those are both horizontals. Here's what I have.
Yeah, that's right, never mind.
If I'm summarizing so far what I have an X-intercept, which is also my Y-intercept. I have a vertical asymptote at 1. And I know that as I go out to the right, my function has to flatten out towards the x-axis. And as I go out to the left, my function also has to flatten out towards the x-axis. Make sense? That's what I have so far. That's all algebra. Well, we used a little calculus here also, right, to get these two in things. All right.
I have a,
Yes.
how do you have an X-intercept if you have a horizontal asymptote in there?
I was hoping you wouldn't ask that. No, I'm saying specifically you because you took me for college algebra. No? Did you? Right? Okay, so see if this rings a bell. I know. See if this rings a bell. When I teach horizontal asymptotes, I always instruct my students to always draw your horizontal asymptotes just at the edges. And to never continue your horizontal asymptote all the way through. Because what it will make you think is that you can't ever cross it. You're allowed to cross a horizontal asymptote within the interior of the function. The horizontal asymptote only tells you what's happening out here. Okay? So this may go like this. Oh, sorry. It may flatten out over here, but it may come up here and it may go down like that. That's okay. And then on this side, it could do this, or it could do some other things. But the horizontal asymptote is not a line that continues all the way through. It's just edge behavior, end behavior. Now verticals, that you absolutely cannot cross those. All right, you cannot draw your function through those. That ring a bell a little bit? Yeah? Okay.
It just wasn't emphasized enough in college algebra.
I guess I didn't. Next time, I'll actually like hit my students with the ruler. You know, do not draw the horizontal asymptote. Well, look, I mean, it happens a lot. It's very common. In fact, a lot of the tutors in the tutoring labs will draw it all the way through. They'll just draw, and that's very dangerous to me. So, okay, let's continue. 5. Well, when you draw a dotted line across, your instinct is to be not to cross it, right? If you go all the way across with it, you're going to not want to cross it, and you might actually have to. So it's better just draw it at the edges. All right, step 5, we want to know where this function is going up and down, right? So this is where we take the derivative, and we figure out where it's undefined, figure out where it's 0, find our critical numbers, put them on a number line, test points, up, down, all that stuff. This is what we did last class, this is what you did for homework. I'm sure you enjoyed the homework this weekend. Now I'm going to use some different notation, because we don't have f, do we? We have y. So I'm going to write y prime equals, and when I take this derivative, I'm going to need the quotient rule, right? Now take a look real quick at your problems that you have here, your 4 problems. Look at the derivative requirements that you're going to have. First problem, very clean, right? That first problem is just going to prove that you know what the heck you're doing, right? You can take some derivatives, very clean polynomial. Look at the next function, the second one. I'm not, yeah, that's going to be up to you how you take those derivatives. There's multiple methods you could use. Quotient rule would work. Number 3, there's product rule with some chain in there, right? Because you got a square root.
You love square roots, don't you?
They're pretty important to be able to work with square roots. Yeah. You'll be fine. And then number 4 is a trig function. Notice also on number 4 that I gave you a closed interval. I'm going to do one today, hopefully, if I have time, that has a closed interval on it so you can see how to approach that. All right, let's take our derivative. We're going to be quick here. Derivative of the top. 1 times the bottom minus derivative of the bottom times the top all over the bottom squared. This does look familiar, right? So what do we get? Negative 2x cubed minus 1 over x cubed minus 1 squared. There's our first derivative. Do you all agree with that? Yeah. Okay. Now, what we need to do is figure out where this is 0 and where it's undefined. So where is this derivative 0? Well, good for us. It's a fraction already, right? So we just set the top to 0. So negative 2x cubed minus 1 equals 0. And let's just move things around. Take the 1 to the other side, right? Add 1 to both sides. Divide by negative 2. So do you get x cubed equals negative 1/2? Yes? And now I take the cube root. You can take the cube root of a negative number. That's okay. Can't take a square root, but it's cube root, so we're going to say that this is cube root of x cubed on the left, cube root of negative 1/2, like that. You do not have to do plus or minus when you do a cube root. It's just one answer. So x is cube root of negative 1/2. Now I'm going to get my calculator out to figure out what that is as a decimal, because I need to put it on a number line, don't I? I think you cubed it, not cube rooted it. So I'm going to do, like, negative 1/2 on my calculator. That's negative 0.5, right? So once you get negative 0.5 on your calculator, you can raise it, use your caret key, and to do a cube root, you do 1 divided by 3 in parentheses. It depends on your calculator. But I would expect everyone can do a cube root on their calculator. So if you don't know how, you come talk to me. I'll show you on your calculator how to do it. But not today, not in class. So I'm raising that to the 1/3. I'm getting negative 0.79 approximately. Approximately negative 0.79. We all right? Okay. So now I'm going to do a number line. I'm going to plot this. It's cube root of negative 1/2. And that partitions my number line into 2 places. Oh, I've forgotten something, haven't I? What did I forget? Where it doesn't exist. Y prime doesn't exist. Where does it not exist? If x is 1, right? If x is 1. Now, x is 1. This is very important. This has not happened, all right? X is 1 is not in our domain, correct? That's where that vertical asymptote is. But there is something happening on the other side of 1, right? On both sides of 1, we have a graph. So what I'm going to do is I'm going to place 1 here. Where is 1 relative to this? Which side of it? Left side or right side? Should be on the right side, shouldn't it? Because this is positive 1. I'm going to draw a number line here. Do you understand what I'm doing? Yes? Sure? Now watch what I do here. I'm going to box this one. That's a critical number, isn't it? I'm not going to box this one. Now the reason I'm not boxing it is why? What do you think? Because it's not in the domain. So do you remember if we see a function go down and come back up, we say that that's a local minimum, right? But the point that it switches has to be in the domain. So if I see switching down and up here, I'm not going to say that's a minimum because this is not in the domain. So it doesn't satisfy what it requires to be in the minimum, or to be, to be a local minimum. Or if it goes up and then down here, I'm not going to say it's a local max because this is not in the domain of the original function. This number is, so if I do get a switching here, it will be a local max or min. Understand? Okay. But I'm still going to pick 3 test points. Here, here, and here. So give me something over there to the left of this number. -1. Give me something here. 0. Give me something here. 2. And where do these numbers go? Derivative. Right?
Ways to remember which one you plug into the derivatives as opposed to which one you plug into the original function?
The only thing I could really say, there's 2 ways. You just remember, or the other thing is to think about what you're trying to do. You're taking a point, right? If you plug this into the original function, that's just going to give you a y value, isn't it? That's going to tell you where your function is. But if you plug this into the first derivative, that answer is going to tell you whether or not you're going up or down, right? If it's positive, it's up, negative, it's down.
But wouldn't the original equation tell you that as well?
No, it just tells you if the point on the graph is above or below the x-axis. It tells you nothing about whether or not your function's going up or down there. That's what the derivative is for. The derivative tells you the slope of the tangent line, right? And that's what we're interested in here. Where are we going, up or down? So when we plug these in, they need to go into the derivative to give us that information. So I'm going to figure out what happens when I plug in -1. So let's try that in here. That would be, I'll do the work right underneath it. I'm going -2 times -1 cubed minus 1. And what can you tell me about the denominator? No matter what I plug in, it's going to be positive, isn't it? Because it's squared. Y'all agree with that? As long as I don't plug in 1. I'm going to square, it's going to be positive. So the bottom's positive. And we know that if you divide something by a positive number, it doesn't change the sign. Right? Okay, so what's the top? This is -1 cubed. That's -1 right here, isn't it? -1 times -2, positive 2, take away 1, positive. So you get a positive 1 on top. That means that my original function over here is doing what? It's going up. Now you plug in 0. So -2 times 0 cubed minus 1 over, well, we know the bottom is positive, right? So that's going to be 0, take away 1, -1, over positive number is negative still. So f must be going down here. You with me? And now plug in 2. -2 times 2 minus 1 over a positive number. So we again get a negative on top, don't we? Negative on top, positive on the bottom. So my function is going down here still. Y'all good? All right, let's talk about where the function's going up and down now. Where's this function? I put f, damn it, I was trying to avoid it. Can I leave it as f?
Yeah.
All right, look, just put this up here. Just call that thing f of x, and now it's okay. All right?
It's going up from negative.
So f is going up from what?
Negative infinity.
-infinity to that cube root of -1/2, right?
Yes.
Where is f going down?
That same point, cube
From that cube root thing
root to 1, right?
to 1.
And then union again.
Okay, so why split it up?
Because it's undefined, right?
Exactly. If this 1 was in the domain, right? If that 1 was in the domain of the function, I would just put on this piece right here, I would just go from here to infinity. But because I can't include 1, I need to actually break this up into 2 pieces. to 1 union 1 to infinity. And there's so many little subtle details, aren't there? I mean, that you have to pay attention to. That's why I'm giving you this as take home. All right, do we have any local maximums or minimums? We do have a local maximum here because it goes from up to down, and that point is in the domain of the function. So I have a local max, and that happens at that point. Now I'm going to use the decimal. It was what, negative 0.79? Approximately. And now let's plug that into the function, all right? Into the original function. Why the original function here? We're looking for a point on the graph, right? So I'm going to take negative 0.79, plug it in here, and then divide that by crap, I think I messed up. Okay. This is not the best calculator for this. 0.79 negative. So when I do this, when I plug in on the bottom, I'm getting negative 1.4930. On the top, negative 0.79. Okay. Did anybody get like about 0.52? 0.52-ish? 0.53, some 0.529. So I'll just say about 0.53. Good enough? You all happy with that? All right. That is, I believe, step 5 and 6. 6 was to find the local max and mins. Yeah, so local min, we don't have one. We don't have a local min. Because it never goes from down to up, right?
Right. I just realized.
Yeah. All right, we're good? All right, step 7. Sorry, this was 6. 6 was this information right here, all of this. So step 7 is now to do the same thing but with the second derivative. So I've got to take the second derivative. I'll leave the first derivative right there so I can use it to take my second derivative. 7. So second derivative is quotient rule again, right? And it's going to have some chain in it too. What's the derivative of the top?
Negative 6x squared.
Okay, negative 6x squared times the bottom, which is, yes, this ugly thing. X cubed minus 1 squared minus now the derivative of the bottom. Chain rule, right? Derivative of the bottom, you have to take the 2 pops out first. 2 and then x cubed minus 1 to the first power, right? Are we done with the chain rule? No. Derivative, what's inside of that? 3x squared. Are we done? Times the top, which was in parentheses, negative 2x cubed minus 1, right? Wasn't that it? All of it over the bottom squared, which when you square, it becomes 4th power. Is this fun yet? Yeah, that's ugly, huh? Let's clean it up. Now, before you start cleaning away here, I want you to pay attention to a GCF that you have. You have an x cubed minus 1. You have 2 factors of it right here. You have an x cubed minus 1. You have 1 factor of it there, right? And you have an x squared here and an x squared here. How about numbers? Ah, look at this. Negative 6. Negative 6 again. So I can pull out a negative 6x squared times the quantity x cubed minus 1.
Because they're going to multiply.
2 times 3 would be 6, wouldn't it? And then a minus. So I've got negative 6 in both. So here's my GCF. This is equal to negative 6. I've got an x squared. I've got an x cubed minus 1. One factor of it, right? Just one factor. That's my GCF. That's being pulled out of that big, ugly numerator. Now, I'm going to put a bracket, even though it's really not necessary to put a bracket. What is still left? After I pulled all that stuff out, what's still left from this term? X cubed minus 1, just one factor of it, right? So I'm just going to write x cubed minus 1. Okay? When I pull all that GCF out of the second term, which is everything here, the only thing left is this, right? This negative's gone, right? So it's going to become a plus. 2's gone, 3's gone, x squared's gone. That factor's gone. So that's the only thing left, right? So I'm going to put plus in parentheses negative 2x minus 1. All of this over x cubed minus 1 to the 4th. Any questions? Now this, I can cancel one factor here with that and make that a 3, can't I? And now I'm left with negative 6x squared on top. And let's clean up the inside of this. This right here. What would that be if I clean it up? X cubed minus 2x minus 2 over x cubed minus 1 cubed. Now we have an issue. Do y'all see the issue? Well, let's stick with it. Does anyone see the issue now? I mean, that's pretty clean, right?
You dropped the cube on the
Drop the what on the what? Oh, I dropped the cubed. Oh, thank goodness. I'm glad you caught that. Right here. Okay. That cubed right there. Thank you. Because I was looking at that going, crap, how are we going to solve that? Because that's not a quadratic, that's cubic. And so I was about to go to like not partial fractions, to synthetic division to try and factor that. But thank goodness, it's not. Let's re-clean this. Hold on. What does that really turn out to be here? It should be minus x cubed, right? Because it's x cubed here, one of them. Take away two of them, so minus x cubed, and then minus 2. Whew. That really just saved us right there. We good? All right, that's pretty clean. I want to know when that's 0, and I want to know when it's undefined. So let's start with asking when it's 0. So when is y double prime equal to 0? Well, set the top to 0, right? When you set the top to 0, you can set this factor to 0. What's the only thing that would make that factor 0? 0. So x is 0 would be one answer. And then we have to set this to 0, don't we? So I'll take a little more time on that one. This is negative x cubed minus 2 equals 0. This is x cubed equals negative 2. I could get that by just moving the x cubed to the other side. And then cube root. So x is cube root of negative 2. I can do cube root of negative 2, can't I? All right. So I have two critical numbers, don't I? It looks like. Are both of these in the domain of the original function? Yes, okay. I also need to check, when does my second derivative not exist? Here's my second derivative. When does it not exist? At x is 1. That is not in my domain, right? But I'm going to include it on my number line. Whew. All right, here we go. Number line. Go ahead, what? We're doing concavity now. So I'm going to, on the number line, put these in order. Well, I know this is a negative number, don't I?
Yeah.
Okay, so that's going to be like negative, let me do it on my calculator.
Negative 1.25.
1.25? Negative 1.25?
We're doing the
Cube root of negative 2.
negative 1.259.
Everyone okay with that? All right. So there's that one. And then 0 obviously is here. And then 1 is to the right, so 1 is over here. I'm only going to box the 2 that are in the domain. And I'm not going to box the 1. And unfortunately for us, we have 4 test points we got to pick. Something to the left of this, negative 2 will work. Something in between here and here, negative 1. Something between 0 and 1, a half. And finally something over here, 2. And where are these getting plugged in? Second derivative this time. The good news is that you're not going to make that mistake at home, right? That would be something you might make a mistake on in an in-class test, but I don't expect you'll make that mistake at home, because you can refer back to your notes and my lecture videos and my homework videos and everything. So, all right, now the pleasure we have of plugging in stuff. Let's discuss it before we plug things in, because we can make this a little easier. What can you tell me about this entire thing? No matter what I plug in for x, what's that entire thing have to be? Negative, right? You square a number, I don't care what it is, it's going to be positive. I multiply that times negative 6, I've got negative. So when I do this, I'm just going to always say that's a negative times, now this piece I actually have to think about. I actually have to plug in and see what happens. And the bottom, I also have to plug in and figure out what happens. So let's try negative 2 in here. If I do that, let me see if this makes sense to you. I have a negative number out front times, now I'm plugging in negative 2 right here. What's negative 2 cubed? Negative 8, but then negative. Positive 8, take away 2? 6. That's a positive number, isn't it? Over, now plug in negative 2 right here. Negative 2, negative 8, minus 1, negative 9. Negative 9 cubed. It's big, but it's negative, isn't it? So the bottom is negative. So top is negative, bottom's negative, negative over negative is positive. This means my original function, which we'll call f, is concave up here. Now we do this. Yeah, negative on top, negative on bottom, negative over negative, positive. Now negative 1 into that. Again, the front left corner is negative. Let's try negative 1 right here. Negative 1 cubed, negative 1, but then change it, right? So positive 1, take away 2, that's negative. And then on the bottom, negative 1 cubed, negative 1, minus 1, negative 2 cubed is negative 8. So you have a negative on the bottom. Positive on top, negative on the bottom, positive over negative is negative. So f is concave down here. We have an inflection point, don't we? That's an inflection point, because it's part of our domain. Now we get to plug in 1/2. We know the top left is negative. Let's be careful here. Is it positive 1/2? 1/2 cubed. 1/8. Negative. Negative 1/8 minus 2. Negative number. Over. All right. 1/2 cubed. 1/8. What's 1/8 take away 1? It's a negative number, isn't it? Then you cube a negative number. Still negative. Ah, look at that.